In Lesson 8.7, Taylor Polynomials and Approximations, we're going to explore our ability to approximate any type of function using a polynomial function formed by the derivatives of the original function. What I mean by that is we can find a polynomial that looks like a given log function or periodic function, trig function, power function. Really any type of transcendental or non-elementary function can be approximated by a series of terms that we will call a polynomial. Now, the amazing thing about this is we have actually explored this already many months ago when we were learning problems like find the line that's tangent to this graph at this given point. What we were actually doing back then was finding first-degree Taylor polynomials. First degree because they were linear, but nevertheless still approximated the graph at that point. Of course, we learned that the farther out you go along that linear approximation, the worse your approximation comes. Well, that's still going to be the same with Taylor approximations, but we'll take a look at that a little later in this lesson. We really should begin by starting at polynomials that are centered at 0, and we call those Maclaurin polynomials. So why don't we go ahead and define those first, then we'll move on to Taylor polynomials, and then we'll start looking at how much error is built into these approximations. So, what do we mean by a polynomial approximation of a function? Let me show you just a quick example here. Let's say that I have this function here, and I would like to find an approximation, a polynomial approximation to this function right here. Now, there's lots of ways I can do that. We learned a long time ago that I could simply draw a line here. Of course, all I need is the slope, which is the derivative at this point, and the y-intercept, which we can find using special formulas. But a linear approximation is not very good. As soon as I start going away from the point of intersection, the line becomes more or less useless. So what I could do is I could do a quadratic approximation. And perhaps that would be a little better. Sure, it seems a little bit better in that neighborhood. If a quadratic approximation is not enough, then what I can do perhaps is come back and do a quadratic approximation. And sure, that's a lot better right there. So I can keep doing increasingly better approximations by raising the degree of my approximation. Let's see what that formula would look like. Of course, if it was just a line, all we'd really need is f of 0. Now, we do need to introduce a coefficient in here, and we haven't seen this before, but I'm going to put 0 factorial underneath the y-intercept. Now, 0 factorial is defined as 1, so it doesn't really make a difference, but it'll help us to see the pattern. For my linear term, my term with the x in it, for that I'm going to need the slope, so I will just do the derivative of that function at 0. I'll divide that by 1 factorial and include my x. Right there is my linear approximation. Of course, this only works if x equals 0, but it works quite well. Now, if I want to get into better approximations for my quadratic approximation, I'll do the second derivative. I'll divide it by 2 factorial, and that will be my coefficient for my x squared term. And, of course, this would keep up forever and ever and ever. Eventually, when I get to my last term, it will say the nth derivative of f at 0. That will be divided by n factorial, and that will be x to the nth power. So if I want a really good approximation, I can do very high values of n. The problem is the work does get repetitive, as we'll see here in a moment, but the results, and I'll show you the actual graphs of these functions, but the results can get very outstanding very quickly. So this is a pretty cool thing here. We're going to approximate functions using polynomials. And we're going to find these polynomials using derivatives. Let's just go and take a look at our first example and see how this works. So in our first example, I intend to show you how easy forming these Taylor polynomials, or rather Maclaurin polynomials, can actually be. The hardest part of it is simply staying organized. You can see in our first problem here, we want to find a 4th degree Maclaurin polynomial to help approximate the function f of x equals sine pi x. because it is a Maclaurin polynomial, it's assumed that we want this polynomial to be centered at x equals 0. So the hardest part of all this really is that we just need to find a whole bunch of derivatives. So why don't we just go ahead and start that off the bat right here. We have our original function f of x. If we want to find f prime of x, what's the derivative of sine pi of x? Well, clearly that's going to be pi times the cosine pi of x. All right. Now, we'll come back later and evaluate this at 0, because after all, if you look at the definition of a Maclaurin polynomial, all the derivatives are evaluated at 0. So we'll come back to that in just a moment. I like to find all the derivatives first myself, just because once I'm in the groove, I like to stay in the groove and, whatever. So, my second derivative of this, if you work on this yourself, you'll get negative pi squared sine pi x. And let me just go on here. My third derivative, and it's going to get rather repetitive, and this does sometimes get kind of tedious, but it never should be very difficult. And that's my third. If I do my fourth derivative, and this is as far as I'm going to go because we want a fourth degree approximation. So I won't go any further than the fourth derivative. But the fourth derivative will be pi to the fourth sine pi to the x. Now what I'm going to do is I'm going to come back and I'm going to say, okay, what is f of 0? In other words, if I plug 0 in here, what would I get? The sine of 0 is just 0. What is f prime of 0? If I stick 0 into my first derivative, hopefully you look at that and you can see, oh, the cosine of 0 is actually just 1, and I have a pi out front. So f prime of 0 is pi. Now, let me just continue this here. The second derivative at 0, well, we're back to sine again. The third derivative, we're back to cosine now, and the cosine of 0, of course, is 1. And so we'll end up with negative pi cubed. And finally, the fourth derivative, evaluated at 0, and there's our sine again, giving us 0. Now, hopefully you still have the definition for the Maclaurin polynomial in front of you. And if that's the case, let's see what the fourth degree Maclaurin polynomial is going to look like. Of course, the way I do that again is I'm just going to go f of 0 over 0 factorial. I'm going to add that to f prime of 0 over 1 factorial with an x. I'll add that to the second derivative evaluated at 0 over 2 factorial. There's my x squared. Hopefully you're seeing all the connections here. The denominator factorial is the same as the exponent, is the same as how many derivatives I'm doing. So everything kind of fits in together pretty nicely here. So I'm just going to continue this out. I'm almost finished, so it'd be stupid of me to stop at this point. And my fourth degree Maclaurin polynomial is going to look just like this. Now, let's go ahead and actually see what this is. If we go ahead and do this, what I'm going to end up with is my fourth degree Maclaurin polynomial. Well, f of 0 over 0 factorial. Remember that f of 0 was just 0. This term is gone. In fact, where my second derivative is 0, I got 0, so that term is gone. And I also got 0 for my fourth derivative at 0. This term is gone. This fourth degree Maclaurin polynomial is actually only going to have 2 terms. That kind of makes it a little easy for me, but, whatever. This right here, f prime of 0, that I can just pull from right here. I already found that out. So this is going to be pi over 1 factorial, or just pi over 1, with an x there. This term is gone, and now I move on to my third degree term. The third derivative evaluated at 0 is going to give me negative pi cubed. So if I do that, I'll have negative pi cubed all over 3 factorial, which is 3 times 2 times 1. I'm just going to write 6 here. And then this will be x to the third power. So if I go ahead and simplify this a little bit, what I end up with is pi x minus pi cubed over 6 x cubed. Now, I do want you to see what this polynomial approximation looks like when it's graphed alongside the original function, the sine of pi x right here. So let me go ahead and bring up a graph here. All right, there is the sine of pi x. Nothing special. It's periodic. It looks like a sine. It's exactly what you would expect. Now, there's our first degree approximation. It's just the tangent line. We could have done that months ago, nothing special. However, if we want to see our third degree approximation, that will include the line or the linear part and the cubic part, and there's that. Now you can imagine that as we go higher and higher and higher in degrees of this approximation, the thin blue right there will become even better and better and better an approximation for that thick red, which is my original function. Let's go ahead and take a look at one more example here, example B, in which we're only going to use a third degree Maclaurin polynomial, but we won't find any of the terms going to 0, so it actually will take a bit of work. Let's take a look. So our second example is going to be done much like our first example, and for that reason I'm going to kind of breeze through this one, although of course, as usual, I encourage you to pause this video right now and try this problem on your own. It's really done the same way that the first example was. Now, the only semi-difficult part of this problem is finding the first, second, and third derivatives. I'll leave that as an exercise to you, and I will simply give the results here. We already have f of x. F prime of x in this case, and you can verify this, like I said, for yourself, but it should be 1 over x plus 1 squared. If I want to find the second derivative of x, what I should end up with here is negative 2 over x plus 1 cubed. And finally, for my third derivative, which is as high as I'm going to go for this problem, in that it's only looking for a third degree Maclaurin polynomial. So my third derivative here would actually be 6 over x plus 1 to the fourth. And again, you can verify that yourself, but I have found that to be true myself, so hopefully it is correct. Let's go ahead and find the value of each of these derivatives at 0. F of 0, clearly that would give me 0 over 1, and I'll just leave that at 0. So perhaps I did lie earlier when I said none of the terms would be 0. Okay, the first one is. But let's take a look at our first derivative. If I plug 0 in there, I'll end up with 1 over 1. If I plug 0 into my second derivative, I'll end up with negative 2 over 1. And if I plug 0 into my third derivative, hopefully it's obvious to see that I'll end up with 6 over 1. So, with that, let's go ahead and form our third degree Maclaurin polynomial. Of course, I'm going to start with f of 0 over 0 factorial, but f of 0 is 0, so I'm actually going to skip that one. I will start with f prime of 0. So f prime of 0 over 1 factorial with an x there. I will add that to the second derivative at 0 over 2 factorial with x squared. And I'll finish up with this term, the third term. Now, just to be clear, I don't always do this when I'm doing these kind of problems. I'm only doing it because this is the second example, but usually you'll get to the point where you're apt enough, you can just start sticking the numbers in and not having to write out the actual formula each time. So, my third degree Maclaurin, let's go ahead and put it all together here. This term here, my linear term, is simply going to be x. This is going to be 1 over 1 times x. My second term is going to be negative x squared, and I got that because x double prime of 0 is negative 2. I will have positive 2 on the bottom, so those essentially cancel out and just leave me with the negative sign. And then over here, this will be 6 over 3 factorial, which is 6. So I just have my x cubed. That seems like a very, very, very easy polynomial. There's no crazy coefficients, nothing strange going on. And it does behoove us to go ahead and check and see that this does work. So here is the graph of my original function. You can take a look at it just like before. Here is the graph of my linear approximation. Again, this is just y equals x. And here is my quadratic approximation, y equals x minus x squared. You can see it's a better approximation. And finally, here's where we end up, our cubic approximation, y equals x minus x squared plus x cubed. You see it's a pretty good approximation right around where x equals 0. we can certainly explore how good an approximation is and how far out we can go until it starts to become bad, although that is rather subjective. But we'll explore that later in this lesson. To move on, now that we have Maclaurin polynomials down pat, let's go ahead and take a look at Taylor polynomials. Really, the only difference we're going to see is where our polynomial approximation is centered. But it does make the formula a little bit uglier. And let's just spend a couple minutes taking a look at that. All right, so now that we're familiar and happy with Maclaurin polynomials, simply polynomial approximations for a function centered at x equals 0. Now we're going to take a look at Taylor polynomials, which are centered at any value x equals c, we'll call it. In fact, x equals c is given in our definition here, so that fits in pretty well. I'm not going to go through all the theory and draw all the pictures. This works almost exactly the same as Maclaurin polynomials. In fact, I will argue that the Maclaurin polynomials are essentially just a special subset of Taylor polynomials, to where c equals 0. That's really the only thing. So, what does an nth degree Taylor polynomial look like? You're going to notice a lot of similarities here. We're going to start with f of c over 0 factorial. We will add that to the derivative at that value of c over 1 factorial. So we're finding the slope at that point. However, here comes the biggest thing that people always forget. This is not going to be x. We're recentering our polynomial, which you learned to do back in Algebra 2. So instead of x, we're going to have x minus c. All right, so far so good. Our second degree term will be f double prime of c over 2 factorial. And then, of course, here, instead of x squared, I will have x minus c squared. And I will continue adding these terms forever and ever and ever. And eventually, I will get to the term, the nth derivative of f evaluated at c over n factorial. And this will be x minus c to the nth power. So you can see that if we let c equal 0, go back through and look at that formula that we just wrote there. If you let c equal 0, what do you end up with? Well, clearly, you end up with the Maclaurin polynomial that we just learned, which means the Maclaurin and the Taylor polynomials really are not very much different. It's just that the Taylor polynomial might look a little uglier because it's not centered at x equals c. Well, now that we know that, let's take a look at a couple of examples with Taylor polynomials, and you'll see that it really is pretty much the same process. So, because we should already know how to do this problem, I'm just going to give it a cursory run through, kind of throw out some of the derivatives and take a look if we can find the equation of these functions that you see looping around here as we work this problem out. Rather than show you all the graphs at the end, I have chosen to loop them here so that you can see the 0th degree approximation, the 1st degree, 2nd, 3rd degree approximations, 4th degree approximations, and then have it loop. So all of these approximations, if you look carefully, are centered at x equals 2. And that's exactly right. That's where we want this to be centered. And of course, n equals 4. So we do want a 4th degree Taylor polynomial approximation. So in order to do this, we already have f of x. If I want to go ahead and start differentiating, f prime of x in this case is simply going to be negative 4 over x cubed. These are all derivatives that I have worked out earlier to make sure they're correct. F double prime of x is going to be 12 over x to the 4th. These are going to get ugly, but not bad. The third derivative here will be negative 48 over x to the 5th. And finally, our 4th derivative of x, in this case, is going to be 240 over x to the 6th. Now, just like with the Maclaurin polynomials, all I need to do here is stick my value of x into each one of these. Of course, instead of x being 0, which fortunately it's not because none of these would be defined, in this case I'm going to use where x equals 2. That's my c value that you see right there. So, what is f of 2? In this case, f of 2 is 1/2 f prime of 2. In this case, again, I've worked these out earlier. This is going to be negative 1/2 f double prime of 2. These things get ugly, and you might want to start using a calculator at some point. And that's certainly valid. You can do that. The third derivative evaluated at 2. Starting to get real nasty, but actually the fractions are reducing quite nicely. That's negative 3/2. And then finally, our fourth derivative evaluated at 2 is going to give us 15/4. So, what is my Taylor polynomial going to look like here? I'm going to skip the step where I write the formula out. As I said earlier, I kind of already have that worked out. So, if I do this, my fourth degree Taylor polynomial centered at x is simply going to be 1/2, and that comes from my f of 2 over 0 factorial. So 0 factorial doesn't matter. Then I will do f prime of 2 over 1 factorial, which again doesn't really matter. So I'll just have minus 1/2, but I'm not going to put x. I'm going to put x minus 2. Remember, we have recentered the Maclaurin polynomial. We've recentered it to create the Taylor polynomial. So everything must be x minus 2. There will never be just an x hanging out unless I choose to go and multiply everything out, which I'm not going to do. My next term is going to be plus 3 over 4, but I will have a 2 factorial on the bottom this time, so I'm just going to put that there, and I'll go through and evaluate that later and see if it matters. This will be x minus 2 squared, so that is my second degree term. Then what I'll do is I'll come back and I'll go minus 3/2, but with a 3 factorial on bottom, which I will simplify later again, x minus 2 to the third, and then finally I will have 15 over 4 with a 4 factorial, and that will be x minus 2 to the fourth. Now, is it necessary to go through and simplify all these factorials? To be honest, no. It's really not that necessary. But if this is something that you want to graph, a lot of times it does make the graphing easier because the fewer keystrokes you need to put in your calculator, the easier things get. So if we do work this out, we have 1/2 minus 1/2 x minus 2. And now I'm going to go through and start simplifying all these fractions here. This next term will become 3/8 x minus 2 squared. The cubic term will actually just be minus 1/4, if I did my math right, x minus 2 cubed. And then finally, I will end up with plus 5 over 32 x minus 2 to the fourth. So again, we have this looping series of graphs, and each one of those graphs represents a different degree of the Taylor polynomial. Of course, the first one is just a horizontal line at y equals 1/2. Then I get the linear y equals 1/2 minus 1/2 x minus 2, and so on and so on. So hopefully you see that it's a little bit of tedious work, but nothing difficult. Well, let's go ahead and take a look at our example D. So in our last example dealing with Taylor polynomials, before we get to looking at error, we have this function here, f of x equals the cube root of x, that we want to find the polynomial approximation for. Polynomial of the third degree centered at c equals 8. So what is this going to look like? Well, we're going to do this the exact same way that we've done all the other ones. Of course, we already have our f of x, and I'm just going to go ahead and write that again here. I haven't been doing that on the other problems, but I'm going to do it here. So we do have f of x, f prime of x. This is actually a very easy one to differentiate. The difficulty is going to come when we go plugging in 8 for each one of those. That will not be very fun, but, you know, it'll work. It'll be okay. So I'm just going to go ahead and keep differentiating here. Again, I've done all these problems before, so I'm hoping that all of my derivatives are correct. They should be. And so I'm going to end up with this as my first three derivatives. Now, because this polynomial is centered at 8, let me go ahead and evaluate each of these at 8. And this is where the fun comes in. F of 8, not very difficult. f prime of 8, not extremely difficult. That one you should be able to do. I, of course, am going to look over my notes that I've already done. Our second derivative evaluated at 8, and this should say 8 here. Our second derivative evaluated at 8 starts to become a little bit more fun. And by fun, I mean we get the result of negative 1 over 144. And, that's a good time right there. Our third derivative evaluated at 8 tends to be even more fun. This is going to be 5 over 3,456, which, while the denominator is a pretty cool number, it's not a number that probably anybody would have guessed. So there you go. I'm going to skip all the factorials and all the writing out this and that, and I'm just going to go ahead and write our third degree Taylor series for this function. And it's going to look like this. My constant is going to be 2. That came from here. Of course, my constant is 2. My linear term will say 1/12 x minus 8. It would be a 1 factorial on the bottom, but again, 1 factorial is really just 1. This next one would have a 2 factorial on the bottom. So what I'm going to end up with is minus 1 over 288. That is the negative 1 over 144 with a 2 factorial on the bottom. Of course, I'll have x minus 8 squared. And then finally, my last term has the most fun coefficient of all, 3456 times 3 factorial, which is actually going to give us 20,736. Of course, then I have x minus 8 to the third power. So there is my third degree Taylor polynomial. What I have running over here by the side is just a little animation that I created. The thick red is, of course, our original function, y equals cube root of x. And I'm just kind of panning around here. I've actually done the 0th, 1st, 2nd, and 3rd degree polynomials all on this graph. So you can see how they all kind of relate to each other, how they become more and more and more approximate as we increase their degrees. Of course, now we come back to be centered at x equals 8, and you can see that in the neighborhood of x equals 8, they all look pretty good. It's only when we go away that some of these polynomials tend to get real crappy on us. So that being said, why don't we investigate the amount of error that's built into these approximations? Of course, as we said, we can go out on these functions a certain distance before they become bad. And why don't we investigate what bad actually means? So up until this point, we've been finding polynomial approximations to a function. Of course, an approximation implies that there is going to be some amount of error built in. If we didn't want that kind of error, we could find simply what the function is at that value of c and just avoid all this approximation altogether. That usually will be somehow impossible. We'll be given values of a function, but not the function itself, or something along those lines. However, if we did want to find the actual error, some value of c, all we would really have to do is find the magnitude of the difference between that function and its approximation. Again, in some way or another, that usually won't be possible. And if it were possible, why would we do an approximation in the first place? And so what I'm going to do is I'm going to show you what's called the Lagrange error bound. This formula is going to tell us the maximum amount of error at any value x equals c. And we're going to call that the magnitude of the error. The r in this case stands for remainder, but we can just call that error without any loss of generality. So the formula we're going to look at here, and this is going to be rather ugly, so I will explain it, but we're going to look at the maximum magnitude of the next derivative. So I'm going to call this the n plus 1th derivative, evaluated at x, of course. We're going to find the max of that. We're going to divide it by the next factorial, so that'll be n plus 1 factorial. And then, of course, we'll have x minus c to the n plus 1 power. So you can see that essentially what we're doing is finding the next term in the Taylor polynomial and saying that that term represents the maximum amount of error built in here. Now, this whole numerator is kind of difficult to understand. We'll do a couple examples, of course, but all we're really doing is finding the next derivative and finding the maximum magnitude of that derivative between our value of c and the value of whatever x we're trying to approximate at. I'll show you what we mean. Let's go ahead and run a couple examples here. Okay, so for our first error example, we're going to refer back to example B. And in example B, if you recall, we found our, at that time, Maclaurin polynomial to look like this. Of course, you can look back up at example B and verify that this is the case. But we simply found our third degree Maclaurin polynomial to be that. Now, this was completely accurate when centered at x equals 0. Of course, the approximation at 0, p sub 3 of 0 equals 0. And if you go back to the original function, f of 0 equals 0. So at x equals 0, this approximation is exactly correct. However, if we want to look where x is 0.5, how much error will there be at that point? Of course, the further we go away from 0, the more and more error there will be. So here is how we find the Lagrange error bound. What we're going to do is we're going to find the remainder, r sub 3 at 0.5. And the way we're going to do that is we need to actually find our next derivative. Remember, the way this is going to look, it's going to be the max of the fourth derivative, since this was a third degree approximation. So we'll find that. And what we're going to do is we're going to bound that between 0, where our approximation was centered, and 0.5, which is where our error is going to be occurring. We're going to divide that by 4 factorial, which I'm just going to write 24, and then we'll have x to the 4th power, which of course I can stick 0.5 in there and get that. But if I do a little bit of work here, and actually our remainder is going to be less than or equal to that. This is a bound after all. It's not going to be exactly correct. But if we go ahead and do that, so my remainder, or Lagrange error bound here, well, what is our fourth derivative here? Let me go ahead and write this up here. Our fourth derivative of x in this situation is going to be negative 24 over x plus 1 to the 5th power. All right, and what we need to do is find the max of this in the interval 0 to 0.5. Again, 0 is where our approximation, our Maclaurin approximation was centered, and 0.5 is where we're trying to evaluate it. So if we find the max of that, we'll use that in our function here. Now, what is the max of this on this interval? You can do the first derivative test, the second derivative test, or to be perfectly honest, you could use common sense here. If I plug in 0, I'll have a 1 on the bottom. And if I plug in 0.5, I'll have 1.5 to the 5th power on the bottom. Clearly, if I put 1.5 to the 5th power, that'll give me a bigger number in the denominator, and therefore give me a smaller number overall. So my max will occur when x equals 0. In fact, what that max is going to be in this case actually is negative 24. You can verify that yourself. Plug in 0 for x, see what you get. Plug in 0.5 for x, see what you get. And the max here is negative 24. So coming back here, that magnitude then is just going to be positive 24, and I'll divide that by 24. That was the 4 factorial. And then x in this situation is going to be 0.5 to the 4th power. If you work that out, what you're going to get is 0.0625. In other words, our maximum error that will occur at x equals 0.5 is going to be this value right here. This is an approximation. This is not our actual error. This is our error bound. This is the maximum that our error will be. Perhaps you're wondering to yourself, well, I wonder what the error actually is. And if you have a calculator, you can sit down and actually figure this out. It's not extremely difficult. Our actual remainder here, r sub 3 at 0.5, is simply going to be, as I said before, f of 0.5, which with a calculator we can work out, minus the third degree Maclaurin polynomial at 0.5, which, again, with a calculator, we can work out. So f of 0.5, I'll just go ahead and tell you that is 1/3. The approximation at 0.5, I will go ahead and tell you, is 3/8. And if we work that out, we find that our actual error is 0.0416. Now, is that actual error contained within our error bound? It absolutely is. It absolutely is. So again, our error bound doesn't tell us our actual error. It tells us our maximum error. And there you go. Feel free to graph this on your calculator, see that this all works out, and let's take a look at one last example. And so our last example, we're going to work this way exactly the way that we worked our last example, except we need to be cognizant of the fact that in example C, we were dealing with a Taylor polynomial. So we're not just going to be able to use x to some power. It'll have to be x minus c to that power. Now, of course, in example C, we centered our Taylor polynomial at 2. And right here, we're trying to find out how much error there is in approximating f of 2.5 using that Taylor polynomial. Well, let's go ahead and do this. I'm going to go ahead and start by actually finding the fifth derivative. The reason I'm doing this is in example C, it was a fourth degree approximation. So we stopped at our fourth derivative. Let's go ahead and find our fifth derivative. And I will tell you that is negative 1,440 divided by x to the 7th power. And we're going to try to find the max of that on the interval 2 to 2.5, from 2 up to 2.5. Now again, because our only x is in the denominator, it should be clear to you that larger values of x will result in smaller values of this fraction overall. Therefore, if I plug 2 in here, that will give me my max. You can verify that yourself. And what we're going to get for that max is 11 1/4. Again, this occurs at x equals 2. So that is what I'm going to use in the numerator of my Lagrange error bound. So let's go ahead and find our Lagrange error bound. R sub 4 of 2.5 in this case, which is where we're trying to find our error, is going to be contained within the max of the next derivative on that interval, which we just found. That's 11.25. And that was a fifth derivative. So we're going to have 5 factorial on the bottom. 5 factorial is, of course, 120. Then what we're going to have to do is this whole x minus c thing. Well, what is x minus c? X is 2.5. That's where we're trying to evaluate. That's what's here and what's here. That's going to be our x. C is where we centered our polynomial, and that would be at 2. Now I'm putting squared here, but what I should put is to the 5th power. Remember, this is the 5th derivative. I have 5 factorial on the bottom, so the x minus c is raised up to the 5th power. If I go ahead and work all this out, which I certainly invite you to do, what we'll find out is that our error will be bounded by this decimal here. It's 0.00292. What this is telling me is that the error, even though we're half a unit away here, the error is actually going to be very, very, very small. Again, this is our approximation. This is our Lagrange error bound. Now, in many cases, we're not able to find what the actual error is. But because these are just notes and I want you to see what's going on, feel free to pull out a calculator and let's find the actual error. The actual error. So what that's going to say, our actual error will be, again, just like before, f of 2.5 minus our polynomial approximation at 2.5. Now, if we do that, I'll go ahead and tell you right now, f of 2.5 is 0.32. We have a calculator at our disposal right now. We can work that out. And our approximation there is actually 3222265 if I use my calculator correctly. So if I find the magnitude of that, what I find is that my actual error is 0.00226. That's a very, very small error. But if you notice, that is contained within our error bound. And so, once again, Lagrange works out for us. Now, in this lesson, we have gone through and found Maclaurin approximations. That's a polynomial approximation to a function centered at x equals 0. We then generalize that a little bit to finding an approximating polynomial at any value of x. We call that a Taylor polynomial, and we had to be careful that we had x minus c in effect. After that, we found the Lagrange error bound, which will take practice, but after you do it a few times, you'll begin to see that the error bound always contains the true error. So this is not easy stuff. It does take practice. And that being said, take your time and good luck with your assignment 8.7.